Est-ce que je dois parler anglais ou français? French is okay for everybody?
I don't think so. Usually it's English.
Usually there's always one guy.
There is one guy, okay. So, okay. So maybe can I close the door? No? To this. Okay. So hello everybody, my name is Guillaume Baudart. I'm a second year PhD student in the Parcast team at ENS. It's a team who works mostly on synchronous languages and compilations. And today I'm going to present you a joint work with Albert Benveniste and, I'm supervised by Marc Pouzet and Timothy Bourque, if you're interested. And today I'm going to present you a joint work with Albert Benveniste and Timothy Bourque on loosely time-triggered architecture. Okay, so the background of my presentation is the following. So everything starts with Paul Caspi's work when he was consulting for Airbus, and he was studying programming practices of Airbus engineers. And one of the problems the engineers had at that time is how can you deploy a critical synchronous application, so like a plane control command or stuff like that, on a particular kind of distributed architecture that we call here quasi-periodic architecture. This led to 10 years of work on what we call now LTTA, which denotes a middleware, and both the middleware and the quasi-periodic architecture. So the middleware ensures that we can safely deploy the synchronous application. And we also base our work on the study of synchronous model for asynchronous systems, because I come from the synchronous language community, and so I find that everything is much more simpler when you consider a synchronous framework. But we'll see. And the outline of my talk is the following. So first I will define precisely what is an LTTA, so with its two components, quasi-periodic architecture and synchronous applications. And then I will briefly talk about the general framework. So how can we modelize both the architecture and the controllers of the protocols in the same framework. And then I will present the two LTTA protocols, namely BackPressure and TimeBased, before comparing this protocol to clock synchronizations that are becoming more and more common in modern architectures. Okay, so let's start with what is an LTTA. So as I said, we consider a particular kind of architecture where you have a set of so-called quasi-periodic nodes. So they activated almost periodically, which means that the delay between two successive activations of one node is bounded by Tmin and Tmax. We also consider that communication is buffered, so you have a kind of a memory in front of each node here, and a node can sample the content of its input memory to compute the next step. And we also assume that the communication delay is bounded by Tmin and Tmax. So in the entire presentation, T is the period of the node and T the transmission delay. So what happens if one node activates is it sends a value to another node, which is received in the memory here. And then when this node activates, it can sample the content of this memory to compute a new value and send it to another node. Okay. So with this kind of architectures, we already have three main problems. So the first one is overwriting. So if a node sends two values before its reader is activated, you will lose one value, the first one. And at the opposite, if the reader is activated twice between two activations of the sender, you will duplicate a value, so you will read twice the same value. So this is a problem, but it can be fixed if you carefully tune the sampling rate of your node. For example, if you want to avoid loss of values, you can always activate the sender more than the reader. So you can skip some activation of the reader. But there is a third problem, which is combination of signals. So you have here three nodes, A, B, and C. And C wants to compute the combination of A and B. Okay, this is classical in in, for example, a control command. So this is a kind of a voter. So you want to combine the input of two distinct nodes. And the idea is that A is set to false for 4 ticks and then true. And B is set to true for 4 ticks and then false. So what you expect to have this output, which is the combination of the two is always false. But if you sample slightly differently your input memory on node C, you get a peak, which is bad because it does not preserve the semantics of your application. Okay, so this was the architecture that we consider. And now what about application? So we want to deploy a particular kind of application that we call synchronous application, which can be viewed as a network of communicating milli-machines. So do you know milli-machines? No? So a milli-machine is basically an automaton with input and output. So each time you take a transition, you possibly output a value to your environment. So a milli-machine is characterized by an initial state and a transition function that map the current state and a set of and a tuple of inputs to the next step and a tuple of output. Okay, and the natural semantics of such application is that you repeatedly fire the transition function from the initial state, and then you get a function that maps stream of tuples to streams of tuples, so the input and the output. And we can also give another semantic where we consider that it is a function that maps tuple of stream to tuple of stream. So here, the semantic of the application is the sequence of value taken on each variable. So we lose the notion of synchronization between the tuple of input and the tuple of output. Okay, so this is the core of what we can do with scaled list, for example, which is a language used in avionics, for example, by Airbus. So you plug block diagrams in this way. So block diagrams, which are basically mini-machines. And so what we want to do is to preserve the CAN semantics. So, okay. A milli-machine can be composed, so you can plug the output of a milli-machine as the input for another one. And the big problem with a milli-machine is that they are not always reactive, so it's not always possible to fire the transition function. For example, if you have what we call a causality loop, which is a cycle of instantaneous dependency. Because each time you fire the transition function, you do what we call a step. And if you have an instantaneous cycle, so during one step you have a cycle of dependency, the machine is not reactive. So the classic idea to avoid this kind of problem is to forbid dependency cycles. So basically it corresponds to...
Can I ask a question?
Yeah, of course.
You said that the communication is buffered. How come we can have causality?
Okay, so here I'm just describing the applications. So there is no link yet with the architectures. So here you consider that it's a purely synchronous application, so there with instantaneous transmission.
So your application is a composition of milli-machines?
Yeah, exactly.
With rendezvous semantics?
Yeah. And the idea is that we can divide our application into several milli-machines, and we want to run each milli-machine on a distinct node of the architecture, okay, which communicates through buffer communication. And we make another assumption, which is there are no instantaneous dependency between distant nodes, so between the milli-machines that are running on distant nodes. This is to avoid micro-scheduling, so we don't want to say that this node has to go further than this one, then this one, then this one. If we avoid this, we can execute everybody at each step. Okay, and now what are LTTA? So LTTA are both a quasi-periodic architecture and a middleware that ensures the preservation of the semantics of the synchronous application. Okay? So there were different approaches. So the first approaches were based on a discrete abstraction of the architecture, which allows verification, but quickly lead to state explosion and incomplete models. Then the last paper on LTTA unified both LTTA protocol on a single PetriNet framework. But at least for one of the protocol, it's a very complex model and it does not give any implementation. Here, our approach is based on Zelus, which is a synchronous language developed in the Parcas team by Marc Pouzet, between the Parcas team and Rennes. And it allows us in a single language to model both the real-time constraint of the architecture, so the jitter on the period of the nodes and transmission delay, and the discrete behavior of the application and the controller of the node. Besides, it gives us an implementation with simulations, but at this point, it does not allow verification. So now I will describe the general framework. So the idea borrowed from a latency insensitive design community is to encapsulate the application machine here, so which is a Mealy machine, inside a shell wrapper, so which controls the execution of the embedded application. Nodes are always triggered by their local clock, which is quasi-periodic, and the controller controls the execution of the application. So the goal of the controller is twofold. You need to delay the execution of the application machine to be sure that you read the correct input. And you also need to delay the output, so sending the last computed value to the outside, to be sure that all readers already read the previous value. Okay, we communicate via signals because these values are not always defined because they are updated on the logical clocks here. So a signal is simply a pair value and a Boolean flow which indicates whether you are defined or not at the current step. And we store the result of the application machine to delay the emission to the outside. Okay. We can also model links between distant nodes in the same synchronous framework. So the idea is that you add a channel, here a FIFO, that model delayed transmission. So you add a logical clock that models the transmission delay, and this clock actually corresponds to a delayed version of the clock of the sender. So here the FIFO is never empty when you tick because you always tick after a message is received. And each time this clock ticks, you send the first value in the FIFO in memory here. So you overwrite the previous received value. So this model buffered communication. Okay. So what's next? So the challenge now is to design controllers that ensure the semantic preservation. And so historically there were two solutions, BackPressure and LTTA, reminiscent of elastic circuits. So this was introduced by Tripakis and al. In 2008. And another solution that rely on time and waiting mechanism that was introduced by Caspi and Benveniste in 2008. Okay. So now I will focus on the logic of the controllers. Okay. So the BackPressureLTTA is based on a very simple idea, which is called BackPressure CAN network, and it is the most simple control flow protocol that you can imagine. So each time you read a value in the buffer, you acknowledge to the sender by sending a message. An empty message, we say, okay, I've read it. So for example, when J is activated, he sends an acknowledgement. Then I know that the previous value has been read and can send a new value. Okay, BackPressureLTTA is basically the same, except that nodes are triggered by their local clock and not each time they receive a message. So the only difference is that we had a skipping mechanism. So for example, here, if I want to activate I, since there is no acknowledgement here, I just skip. J can be activated because there is a fresh value in his memory. And then if I want to activate J again, he detects that there is no fresh value here, so he needs to skip. And then I can compute a new value, and everything works. So the code is illustrated here. So there is a version in Zelus, but I didn't want to bother you with the syntax of a new language. So, but it exactly reflects the behavior of the code. So what you have is a two-state automaton. In state wait, you wait for fresh input before computing a new step of the embedded machine. And in the ready state, you wait for all readers to read the previous value before sending the new one, the last computed one. Okay? So here it's basically what it says here. So when all your inputs are fresh, you can compute a new value and send an acknowledgement saying, OK, I've read the value. And in ready state, when you receive all the acknowledgement of your receiver, you can safely emit the new computed value. And we have three theorems about this simple protocol. So first, the composition of the controller and the embedded machine is always well defined. So this is one advantage of our approach, is that both the controller can also be viewed as a melee machine because it is expressed in a synchronous language, in a simple synchronous language. And so we can check that composing the controller with the embedded melee machine does not introduce causality cycles. So this clarifies the link between controller and application. The third theorem is that Back-PressureLTTA preserves the CAN semantic, which is what we want. So the idea is that you can forget the skips. So you just read the emission of each node, and it corresponds to what we expect because you always wait for fresh input and you never overwrite a value. And finally, the worst case throughput is 2 Tmax plus Tomax. Okay. Now, why do we want another solution? So the main problem with back-pressure is that apart the fact that it multiplies the number of messages and memories, it also blocks whenever a node crashes. So as soon as the node crashes, it can't send acknowledgement anymore, and the entire network is stuck. So the idea is to replace back-pressure by a waiting mechanism using the timing characteristic of the architecture. So basically, the idea is that when you are in the wait state, for example, you know that if you wait long enough, you are sure that you have fresh inputs in your memory. So the first solution was introduced in 2008, and the idea here was to mimic a synchronous architecture and so to impose global synchronization throughout the entire architecture. So you mimic synchronous steps. And our proposal is to relax this solution. So we localize synchronization, and we don't need a broadcast assumption anymore because this solution is based on the fact that every node sends a value to every other node and see the publication of all other nodes. So broadcast communication. Okay. So again, node alternate between execution and publication. And we assume that a sender sees the publication of its receivers. Okay. And as I said, at some point, a node can be sure by waiting that the last send data has been read and that fresh value is available in the memory. So the code is the following. So here you add an internal counter, n, which is initialized with value p here and then decremented at each tick. So this is a synchronous way in Lustre to say you decrement a counter initialized with p here. And so when n reaches 0, which means that the previous value reaches 1, you can emit IM, which triggers a step of the embedded machines. And then you are in state ready, and you reinitialize your counter to the value q and decrement it at each step. And when n reaches 1, you can go in the wait state again. And the idea is when you detect a publication in your environment, so either from your sender or from your receiver, you can bypass the waiting mechanism here because you are already late and you know that you can safely emit your output. Okay, so I have a small animation to show how it works. So assume that you have a pair sender-receiver here, and assume that the receiver is the first to send a value. So the sender notices this publication. So here I model the transmission delay here. So this value is received here. And then they decrement their internal counter because they are in the wait state. And the only way to go from wait to ready is to reach 0. And at some point, the sender reaches 0 and executes a step of its embedded machine. Then the receiver executes a step, and they decrement their counters. And now the sender sent a new value, and even though the receiver has not yet reached 0, it noticed the publication and sent a new value. So as you can see, there is a clean alternation between publication phases and execution phases, and it's why it works, why the protocol works. So again, we have 3 theorems. So first, the composition of the controller and the embedded machine is always well defined. So the controller, again, does not introduce a causality cycle. Second, the time-based preserves the Kant semantic of the embedded application. And I will detail the proof of this theorem in the next slides. And finally, we have a result on the worst case throughput, which depends on the initial value of the counters, P and Q. So the precise statement of the second theorem is the following. So you need to ensure this condition on the initial value of the counter to preserve the semantics. And the proof sketch is this one. So we do worst case reasoning. So we basically say that at worst, this value will be received at this time, and so we need to wait at least that time. And we are tuning constant P and Q to ensure that the receiver always reads the proper data. So what does it mean that the receiver always reads the proper data? So it's equivalent to 2 properties. So the first property is that so if you have 2 nodes, A and B, where A produces value for B, it means that the value published during the k-1th round by A is always received in the shared memory before the kth execution of B. Okay? So the worst case occurs when B is the first to publish his k-1th value. At worst, the A will notice this publication Tmax plus Tmax later. So this corresponds to the scenario where A is activated just before the message is received in the memory, so Tmax later. So you need another Tmax to read the value. Okay? And then in the worst case, this publication is received in the memory Tmax later. In the meantime, B activates as fast as possible, and so it will execute ptmin later. And so we read B reads the proper value if the top path is always shorter than the bottom one. Okay, this gives the first condition on P. And the second property is that the kth execution of B always occurs before the next publication of A. So you read the correct value. And now the worst case is when A is the first to publish the k-1th value and then execute as fast as possible. So the next write occurs P plus Q tmin later and is received at best in the shared memory tomin later. In the meantime, B notices in the worst case the first publication of A Tmax plus Tmax later and then activates as slow as possible, and so P Tmax later it executes. And here again we read the correct value if the top path is always greater than the bottom one. Okay, so this gives a second condition on Q. And an interesting corollary that you showed on the short animation is that the protocol ensures a clean alternation between execution and publication phases for each pair of communicating nodes. And so now if we assume on top of that we have a broadcast communication, since every node is a producer for all other nodes, you find again the result of Benveniste and Caspi, which is you mimic a synchronous execution through the entire architecture. You have global synchronization barriers. Okay, so now we can compare the two protocols. So first of all, they really look alike. And they are both two-state automaton. As this is not random, this is due to the nature of the controller, which is on the one hand, you delay the execution of the embedded machine to be sure that you read the proper input. And on the other hand, you delay the publication of the last computed value to be sure that the previous one has been read. Okay? So you wait for a new value and you are ready to send the other value. So in more detail,
can you show where in these two automata you have a delay? It's not clear that it's
a delay.
You said you delay until some condition.
Oh yeah, so here you wait, so each time you are activating, you stay in the state wait until you see fresh value from all output. So here you are waiting. Here it's the same, you stay in state ready until you see a fresh value, a fresh acknowledgement from all your receiver.
So the tick is synchronous. The tick, the clock is considered to be really periodic.
No, not at all. It's just that this controller is only activated on the tick of this clock.
Yes, but is there any relation between the ticks of the different...
No, that's the point. So you have a communication through memories here, and you have a mechanism, a bit alternating protocol to test if there is a fresh value in your memory. So you don't need synchronization between nodes.
My question is there a drift between the clocks, or
yeah.
They fluctuate?
Yeah. Because so you recall that the clocks here are quasi-periodic, so they are activated between T-mix. The delay between two successive activations is bounded.
There is a guarantee that they can drift, but...
No, they can drift arbitrary they can drift arbitrary because if assume that this guy always goes at T-min, and this one always at T-max, you can't bound the difference. So the idea is that you wait for a message to resynchronize the two at some point. But there is no relation between the clocks of distinct nodes.
Maybe I can give a comment on the context. The point is that in contrast to telecom, where you favor synchronization over time, you like to get all packets, and you resend if needed, in TCP, for instance. In distributed control, this is a bad idea. What you want is to get the most recent value for the data. You don't care if you do continuous control regulation. And you don't care about losing some data, and you don't care about using twice the same. Okay, so for continuous control, what the people do is that you can have your own local clock. They don't need to be synchronized. You read when you read, you write when you write, and in some sense the communication medium can behave the same. In the AFDX networks that are embedded on aircraft, the network decides itself when to fetch the data. So there is no collision because the network decides to take the data from somewhere and to fetch it. Okay, so and the whole philosophy is always to have protocols that will never lead to any kind of blocking. Because this is, you want the architecture to survive anything. Okay? And therefore, depending on what you deploy on top of this architecture, you need to compensate for the artifacts that result from that, or you don't. If you do continuous feedback control, then in some sense the physics is continuous. Okay, and you don't care about losing or duplicating data, and therefore you do nothing. You just use this kind of architecture, brute force, and you deal with it. And the robustness of the control gives the right answer. Now, if you look into the discrete protection mechanism or mode handling, these are discrete machinery for which there is no continuity, and therefore having the right synchronization throughout, between preserving the right synchronization from the spec down to the implementation becomes important. And so the game is still to use the same kind of architecture and try to ensure that you are never leading the implementation to diverge to something that was not expected.
Yeah.
And this is the whole purpose of those mechanisms, which tell you that you can run an application that is logically synchronous on top of an architecture that is not synchronized at all. Okay? And this is why you have to do something to ensure that.
Another way to see this is that you have a synchronous program on each node, okay, and they are activating, so they do a step of this synchronous program at each tick of their local clock, and then they send value to the outside on the tick of their local clocks, and so there is no synchronization between nodes, so the values are stored in a buffer. Okay, and then another node, when activated on its own local clock, can check the value in the memory, and if it was expecting, it can do the transition or not. So you have an island of synchronous programs that are linked by buffer. If you want.
Okay. So excuse me, to be sure to get it. So these two algorithms are very similar in the sense that the BackPressure just waits indefinitely, so that may be a problem because if you're keeping and never receive something fresh, then you start.
Yeah.
While in this case, you upper bound the number of clocks that you will wait before transitioning anyway in a wait state, so overwriting a value at one point in time. And so P and Q, you are determining them in some optimal way, so to ensure
that you will never do something wrong. So, okay, so it's a worst case, to preserve the semantics.
To preserve the semantic, okay. And the reason why P and Q, because they, in terms of throughput, waiting there, waiting in P, waiting in Q doesn't affect anything, but in terms of correctness, the semantic correctness, there is an impact. Yeah. And this is why they are different, because you want to be sure to read things when they are written, or what's the, so why P and Q
are important?
Why they are not the same?
So, why they are not the same?
So an intuitive, physical, if you want, meaning why they are not.
Okay, so so the easy answer is that they are not the same because here you can make a shortcut here, and here you have to wait.
Okay.
And
now this is when when you can have a Q prime which is more than Q when some new data comes and then you go. But already the parameters you set in the previous formula that were determined to ensure the correctness of the system are different.
Yes, they are different. I can go back here. Here you have the formula, so here the idea is that you just wait for all possible publication. You know that at some point the publication starts and you wait for all other publication. And here it's a bit more tricky because you don't start decrementing the counter from Q when you detect a fresh value. You start it when you make the transition from the state wait to the state ready. So it's not triggered by an external signal, it's triggered by your own logic. So
perhaps to get the intuition, the token-based mechanism is like in PetriNet, so it's like in pure max plus algebra, where you wait for having received all tokens before firing. Okay, and this mechanism does two different things. The first one is that to be sure that one cannot be too fast, you make everybody waiting, but you don't want to wait too much.
Yeah.
So you need both to slow down the people so no one is going too fast, and to accelerate the people, and this you do by observing the publication of other people. So it's a mixed token time-based mechanism that we are using.
but what?
Acceleration is by token-based, and slowing down is by time-based, and this is the way that you avoid blocking, because you never get stuck waiting for tokens.
But one thing is true is that you can always take for both for P and Q the maximum of the two, because you do worst case reasoning, so you can wait more than necessary. But this is the best of the worst case possibility. So these bounds are optimal in other terms. Okay. So a little bit more on the comparison. So as I said, the BackPressure protocol is very flexible because it does not require the timing specification of the architecture, whereas the TimeBased entirely rely on these constraints, because you need Tmin, Tmax, and Tomin, Tomax to compute P and Q. The BackPressure is not very robust, since as soon as a node crashes, the entire network is stuck, whereas the time-based protocol can run in a degraded mode, because if a node is stuck, you just compute with the last emitted value by this node. Because as soon as your internal counter reaches 0, you can make a transition. So this allows to program fault tolerance policies directly in the application for the time-based protocol. And for the BackPressure, you need to implement in the middleware some kind of resurrection protocol to be sure that the node will not be stuck forever, which can be tricky. TimeBased and BackPressure works on any possible communication graph, so there is no restriction. And in terms of pipelining, BackPressure is a kind of optimal solution in the sense that you never wait for distant nodes. As soon as you get a fresh value, you can compute a new step. The time-based offer a limited version of pipelining because pairs of consumer and producer are somehow tightly synchronized, because there are a clean alternation between execution phases and execution and publication phases between sender consumer. But still, there is no reason to wait for something that is very distant from you. And so we work mostly on these two points here, compared to the previous proposals. So now, what about clock synchronization? So clock synchronization are becoming more and more common now in modern architecture, and one might wonder why bother with LTTA, since we can do easily clock synchronization and everything becomes easy. So to answer this question, we try to implement a clock synchronization protocol on a quasi-periodic architecture to fairly compare the two approaches, and we give the advantage to the adversary because we use the most efficient protocol for comparison purposes, so the most simple possible clock synchronization algorithm. So one node is used as a time reference for all other nodes, called the central master clock, and this central master clock broadcasts its time reference to all other nodes, so they will synchronize on one node, which is not very robust. But so the big picture is the following. You have here synchronization interval. So this is the interval at which the clock master sends a new reference. And in green, you have the time of the clock master. During the synchronization interval, local clock may drift from this reference. and then they are resynchronized here. The offset after resynchronization basically corresponds to the difference between the worst possible transmission delay and the best possible transmission delay. And then at the end you have the maximum divergence, and you can compute the precision of such an algorithm. So on a quasi-periodic architecture, assuming a synchronization interval of R, the offset after resynchronization is the difference between the worst case scenario before receiving a value that we talked about earlier and the best possible transmission delay. You can compute the drift rate in terms of Tmax and Tmin, and the maximum divergence and the precision, the global precision of your algorithm. Now, given the precision of your synchronization protocol, you can build a global notion of times or macrosteps. So the idea is that nodes subsample their local clocks. So they only execute on a subsampling of their local clocks. And if the distance between two macrosteps is more than the precision, you are sure that you approximately have the same time tag as the other node. And now lockstep execution can be achieved if node execute once over 4 macrosteps. So this is because even when the best possible synchronization algorithm, time tag for one event can the time tag of a single event on 2 distinct nodes can always differ from 1. And so it can be plus or minus 1, so you need 3 ticks to ensure the preservation of the order of the event on each node, and then you wait for another tick to stabilize everything. And we also need to wait for the transmission delay. So for example, if the transmission delay is significant compared to the period of the nodes, you need to wait to be sure that you have a new value before executing. So it's not enough to wait for 4 macro steps, you also need to wait for a new value. Okay. And now we can compare the overhead of the 3 protocols compared to an ideal synchronous execution. So an ideal synchronous execution is when every nodes are periodically activated with a nominal period, which is Tmin plus Tmax over 2, and where there is no jitter in the transmission delay. So the first case is when the nodes are very slow compared to the transmission delay. And here you can see that the overhead of the back pressure is 50% and 75% for both time-based and global clock protocol. So here what we can see is that the back pressure is always better than the 2 other protocols, and that the 2 other protocols are basically equivalent. Okay, so now if the period of the node is at the same order of the transmission delay, all protocols are basically show equivalent performances. And the last case is when the nodes are significantly faster than the transmission delay. And here what is interesting is that clock synchronization comes for free, because this is a base case for clock synchronization. And you see that protocols are basically equivalent if the jitter is limited. And then clock synchronization complexity explodes when the jitter increases. Okay. So to conclude, we presented a new model. So we can present in the same synchronous framework both protocols, and we claim that it simplifies and clarifies the model of previous paper. We gave a new proposition for the time-based protocol that allows for pipelining and do not require global synchronization. We have a model of the architecture and of the protocol in the same language, which allows for easy simulations. And we compared our protocol with clock synchronization deployed on the same architecture to see what are when it is useful to, when do you want to use LTTA. So basically when the nodes are slow and the transmission delay is relatively small, And this is basically the case for control applications. Thank you for your attention. If you have any questions. Yeah.
I'm not aware of these kind of problems, so maybe the thing that I would say is very stupid, but just to understand. So you said that in these kind of systems you have one problem that is using a bug value.
Yeah.
That can mean using an old value because you read it twice,
yeah.
or using or overriding a value. So
yeah.
And to solve this, you use a time delay.
Yeah.
In the two solutions, you use delay.
Yeah.
But what if you use, for example, a sequence number? You add the sequence number to each message.
Yeah, but it doesn't prevent you from overwriting a value.
No, because if you receive two values, these two values have a different sequence number.
Yeah, but you only have one buffer.
Because you can only host one value.
Yeah, and even if you can host several values, since the drift between distant clocks are not bounded, you will need an infinite buffer.
I understand. Okay. But maybe if you consider buffers that are more than 1 unit, you can
optimize.
Be more flexible on the time, on the waiting time, so you can achieve better.
That's a good question, and so the idea is that if you have a buffer of size n, for example, maybe you can relax the timing. So this is not true for the BackPressure protocol because you react as soon as you have a new value.
Yeah.
And for the time-based, I'm not sure it will help because So the idea is that you simply replace the BackPressure link by waiting.
Yeah, I think his idea is interesting in the sense that you can use it to preserve the order of the message even if the channel does not do it.
Yeah.
But the very constraint is that all memory must be finite.
Yeah.
And usually not huge.
So
that is the very constraint. But of course you can recreate the right ordering of the messages by using stamping.
And sorry, but it won't work because for every application, because here we don't want to make any assumption on our application. And so, for example, if you have a feedback loop, so if you have A that depends on B, A that depends on B, and B that depends on A, you will need to wait for the new value of B before sending the second one. So a buffer of size 2 is not useful here, because it will never be full. Because here, you send the first value.
Yeah, and sequence number 1.
Yeah, and then B needs this value to execute one step. Yeah. And A needs the value produced by B to send.
Number 2. So B reads sequence number 1 and produces a message with sequence number 2.
Yeah, here.
Yeah.
So this one is read.
Sequence number 2 and produce a message with sequence number 2.
Yeah, with sequence number 3. But you see that the previous value has already been read here.
Yeah.
So you don't need to store it.
Yeah, of course.
So a buffer of size 1 is enough, and actually you don't need buffer of size more than 1 if you have a feedback loop like that. And this is not an assumption we are willing to do on application.
A question about the overhead.
Yeah.
What you're measuring in terms of overhead is basically the amount of time you spend waiting to ensure the synchronization.
Yeah, compare basically the amount of tick you need to wait before.
So if you would increase the amount of buffering, you would increase the overhead. If in the case which is useful, to avoid overwriting state, you would increase the overhead further.
For me, you would decrease the overhead.
What you can do is that if there is no dependency, there is no feedback like that, you can say that you can send more value, so to fill this. And it's kind of equivalent to dividing the transmission delay by the number of messages you are sending. So this is taken in account in the initial value, for example, of the time-based protocol. And for the BackPressure, you see that you have a fresh value, and you can execute for all value you have in the queue. So basically, you divide the transmission delay by the length of your buffer.
Clarification when you use broadcast.
Yeah.
So is it you're referring to a broadcast medium, or you want to disseminate some information to everybody, to all the nodes?
Whatever.
No. Yeah. So what I was.
Because there may be a difference. So if you have broadcast medium, then you have contention when you try to access the medium. So.
Yeah, we.
To understand what's.
No.
I told you the very basic principle is that in those beasts you never create elements in the architecture that would create contention or blocking or whatever. So they always avoid that. So, for instance, transmission links would never be passive. Because usually when you try to enter a link, you may have to handle the collision.
Yeah.
If you have a collision, you have a failure to access the medium and you retry. Okay, so Aloha is the whole story about that. Okay, but in those architecture, the link is a master of itself. That's why you have those desynchronized techniques, because all the link can do is to decide to fetch something. So you fetch what it has, and therefore the writing inside the buffer of the link is something that is desynchronized from the work of the link itself.
So basically, if you have a complex...
the way that the idea is always to avoid any risk of blocking of the whole architecture through the failure of one part of it.
Yeah, and another...
So this is essential. That makes it very different from telecom networks.
In the link model, there was a buffer, so before waiting, you wait for the link to be clear.
Yeah.
But one way you cannot exceed like 25% capacity of the network, because it's 75% it's over.
Yeah.
And the link is back pressure. Is it forbidding you to?
That's why we cannot use pure back pressure, because pure back pressure is Petri-net, so it is potentially blocking. Okay, so it's an even graph, essentially. It's an express system, and therefore it is potentially blocking, and they don't want this, so they have to have escapes.
But another idea is that we model the most simple link, we model the most simple links, and if you have more complex communication medium, you can either put it in the transmission delay bounds, or you can consider that it's a LTTA node on its own, triggered by its own local clock and stuff like that. So because our model of architecture is very abstract, you can put a complex communication link inside the bound, or if it's more complex than that, like you have one node that centralizes all messages before broadcasting everywhere, you can always consider that the communication medium is another LTTR node. Okay.
Just to be sure, can you imagine some application where one of the nodes is twice faster than the other one, like one task if you compare to the asynchronous multitasking approach?
Yeah, so for example, if you have a jitter of 30% on the period of the node, so you have basically Tmin over Tmax, which is approximately 2. And if one node is activated each Tmin and another one each Tmax, you have a difference of speed of a factor 2. But then the protocol ensures that the fastest node will slow down to wait for value from the slowest one.
I don't think this is the question. That's not
Okay.
my understanding. What you want to say is that even when looking at the synchronous application, the spec of the computation, the model that we took is that everybody would be doing, every main machine would work at each step.
Yeah.
Yes, and the steps are kind of close
Right.
in time.
And of course this can be relaxed, but this is the whole story about synchronous languages, meaning that instead of having everybody being active at every logical tick, you can have logical clocks corresponding to event-based downsampling or even also event-based upsampling, and where you can have slow task, slow activity and fast activity depending upon particular trigger signals. It doesn't change. I mean, it's a little bit of you know, syntactic sugar on top of that, but it's in some sense a separate issue that you solve before doing this reasoning. So these are two separate issues, and you can combine both, of course.
And why do you don't you try to preserve the other semantics? You said you want to preserve just the can semantics.
Okay, because
if you want to work on correlated values, you want the other semantics, and in some applications you want to that each node works on correlated values.
No, but the idea is that you will never be able to preserve the synchronization on all variables. So if you consider your application as one single Mealy machine, the first semantics is that each new value at each step, you immediately compute the new value for all variables. And since nodes are not synchronized, this is impossible. So what you can do is that if you need to preserve the tight synchronization between some values, you will need to compute them in a single node. But otherwise, you can't preserve it.
No, essentially, what it says is that you create a node that does the combination of the two variables, and you add it to the network, and the protocol does what is needed. So it's just by requesting that you want to combine them that the protocol does it for you.
No, but even if you want to combine them, you will never be able to ensure that the computation was done at the same time.
No, but you don't care.
No, yes, that's what I said. We don't care.
That is what is important. That's what you are interested in. Timing is never an issue, in some sense.
You want the speed and the pressure that you are computing correspond to the same point in time. For instance, if you want to do this kind of application.
Yeah. And I think it's not possible if variables are computed on distinct nodes, because nodes are not synchronized. But you can bound the delay between the computation of one variable compared to the other one. Because you have the worst case throughput, so you can bound the length of one step.
Okay. So the time is up, so if you want to keep exchanging, don't be shy. Thanks for the talk.
Thank you. Thank you for the invitation and your patience. So.